Let's begin with the aftermath of the heavy rain that's been felt across the United Arab Emirates and some neighbouring Gulf countries, a region usually known for its hot and arid climate.
Many experts are pointing their fingers at large-scale and undercover operations at the Large Hadron Collider that could be influencing unusual weather patterns, including the unexpected storm in Dubai. This controversial theory connects the depths of particle physics to changes in global weather, stirring intense debate. Using powerful magnets, the Large Hadron Collider speeds up particles to collide, unlocking secrets of the universe like the moments after the Big Bang. But now, something has gone terribly wrong. In Dubai, fierce thunderstorms and heavy rains are unleashing chaos, threatening to disrupt the fragile balance of life on Earth. What unknown dangers have we wakened from the universe's depths? Join us as we desperately seek the cause behind the dangerous catastrophe in Dubai. Dubai just nearly submerged. The Large Hadron Collider is the world's largest particle accelerator with a circumference of 16.7 miles. It is situated approximately 328 feet underground to avoid external environmental factors like surface vibrations or electromagnetic interference from nearby vehicles and electronics, which could corrupt the experimental data. Scientific, practical, and economic factors influence the decision to place the Large Hadron Collider beneath the Earth's surface in the Geneva Basin. The Jura Mountains to the north of Geneva present challenging terrain, and tunneling at this depth helped avoid the higher costs of digging through them. This subterranean placement also helped reduce land acquisition expenses, given the high property values in this scenic area near a major Swiss city. Positioning the collider underground offered additional advantages, such as a stable, controlled environment essential for the precision required in its experiments. This depth protects the collider from cosmic rays, high-energy particles from space that could disrupt the sensitive measurements. Furthermore, the underground temperature is relatively constant, unlike on the surface where it can fluctuate significantly. This consistency is crucial for maintaining the operating temperature of the superconducting magnets, about -456.25 degrees Fahrenheit, necessary for their efficient function without electrical resistance. It's more than enough for any fails to produce such a massive storm in the middle of the desert like it happened in Dubai. Dubai recently experienced a huge storm that brought an unusual amount of heavy rainfall, flooding, and disruptions, which is quite rare considering the city's usual dry, desert climate. Normally, Dubai gets only about 2.7 inches of precipitation every year. However, during this storm, the rainfall exceeded 4.75 inches. This is a significant amount of rain for an area not used to such weather, leading to widespread flooding. Roads, homes, and even the Dubai International Airport were heavily affected. The airport, a major global travel hub, had to divert flights and faced considerable operational disruptions. The storm was part of a broader weather pattern affecting the region, which included not just rain, but also lightning and thunder. This kind of intense weather event is uncommon in the UAE, which typically enjoys clear skies and minimal rainfall throughout the year. The flooding was severe enough to submerge cars and damage infrastructure. Emergency services were on high alert, navigating through the flooded streets to assist affected areas. Schools, offices, and government buildings were closed to ensure safety. The local weather authorities had issued several alerts warning of the severe conditions, indicating the seriousness of the storm. This event caused significant disruption to daily life and raised questions about how well-equipped cities like Dubai, known for their harsh desert climates, are to handle such rare but extreme weather events. These superconducting magnets are critical for guiding the high-energy protons at speeds close to that of light, around the accelerator's ring. Each magnet, cooled with liquid helium, is designed to bend the particle beams accurately. Without the effective performance of these superconductors, achieving the necessary collision rates for the experiments would be impossible. The Large Hadron Collider directs two high-energy particle beams in opposite directions within the same magnetic field but in separate beam pipes. These beams collide at 4 points, which are the sites of the Large Hadron Collider's main experiments: ALICE, ATLAS, CMS, and the Large Hadron Collider. These experiments aim to validate various theories of particle physics, including the properties of the Higgs boson, which are crucial to understanding particle mass. The Large Hadron Collider can create collisions at energies up to 14 trillion electron volts when active. These high-energy collisions mimic conditions a fraction of a second after the Big Bang, enabling physicists to explore the structure of space and time more deeply. The Large Hadron Collider also studies dark matter, an elusive substance that doesn't emit light or energy and is invisible to current technology. It helps scientists deduce the properties of dark matter from the behavior of visible particles affected by its gravitational pull. Constructing the Large Hadron Collider was a monumental effort, requiring the removal of millions of cubic feet of rock to accommodate the twin beam pipes and the powerful magnets. This international project brought together engineers, technicians, and physicists worldwide to share their skills and labor. The data collection systems of the Large Hadron Collider are equally sophisticated. Equipped with thousands of detectors, they capture the debris from each collision, particles that exist only briefly before decaying. These detectors must collect data swiftly and precisely, demanding the most advanced technology and continuous innovation. From its inception in 2008, the Large Hadron Collider quickly revolutionized our understanding of the universe's fundamental particles and forces. By 2010, it had achieved a milestone by propelling protons to energy levels of 3.5 trillion electron volts, nearly quadrupling the capacity of earlier colliders like the United States' trillion electron volts. In these initial phases, the Large Hadron Collider enabled scientists to observe collisions of high-energy protons, aiming to replicate the early universe's conditions shortly after the Big Bang. By colliding protons at such high energies, researchers sought to recreate and study the quark-gluon plasma, a state of matter believed to have existed right after the Big Bang. These 3.5 trillion electron volts collisions paved the way for the discovery of the Higgs boson, fundamental to the standard model of particle physics, responsible for giving mass to elementary particles. In 2012, the European Organization for Nuclear Research that houses the Large Hadron Collider scientists identified a particle consistent with the Higgs boson, highlighting the Large Hadron Collider's crucial role in physics. Further upgrades were necessary to probe deeper into the universe's fabric and investigate physics beyond the standard model. Thus, the Large Hadron Collider underwent several improvements to increase its collision energy. By 2015, the Large Hadron Collider had resumed operations with significant upgrades, achieving 6.5 trillion electron volts per beam, almost doubling its original high-energy record, resulting in a total collision energy of 13 trillion electron volts. At this level, the Large Hadron Collider not only confirmed the Higgs boson's existence, but also opened avenues for discovering new particles and exploring the primordial universe's conditions. The boost to 6.5 trillion electron volts per beam meant particles were propelled to 99.9999991% of light speed. This extreme speed was crucial for increasing the likelihood of generating rare particles and phenomena during the collisions. These 13 trillion electron volts collisions generated vast amounts of data, vital for physicists analyzing the results of these high-energy encounters. Sophisticated detectors around the collision points, ATLAS, CMS, ALICE, and Large Hadron Collider, recorded the emerging particles. Each detector, like ATLAS and CMS, had a specific focus, which was essential for discovering the Higgs boson and conducting broad particle physics research. While the European Organization for Nuclear Research that houses the Large Hadron Collider's creation is a behemoth of scientific and engineering achievement, its recent operations have plunged the physics community into excited confusion. Upon maximizing the Large Hadron Collider's energy output, scientists encountered unexpected results, data that defied easy explanation and spurred a flurry of speculative theories among top scientists. These mysterious findings have implications for our current understanding of particle physics and the future direction of scientific exploration. Is this just a calibration error, a minor glitch in this complex machine, or are we on the brink of a discovery profound enough to rewrite textbooks? With these questions unresolved, the global scientific community is watching eagerly yet anxiously for what revelations might come from this underground giant. What other secrets does the universe still hide, and what new tools besides the Large Hadron Collider might we need to uncover them? Next, we dig deeper into the Large Hadron Collider, uncovering how it uncovers the secrets of the universe from beneath the Earth. The subatomic search for the God particle. In this vast subterranean complex, 7 advanced detectors stand ready, each precisely designed to capture the chaos that ensues when subatomic particles are accelerated to nearly the speed of light and then collide. While proton beams are usually the particles of choice, the focus shifts to lead ions for 1 month each year. This shift marks a significant event for the collider regarding physical weight and scientific implications. The elaborate arrangement of the large particle colliders serves a much greater purpose than mere spectacle. At its core, the Large Particle Collider functions as a crucial experimental ground for probing the universe's fundamental forces. Physicists employ the collider to test and explore various theoretical models that at first glance might appear extravagant or purely speculative. A key focus of these tests is the Standard Model of Particle Physics, which provides a framework for understanding how the universe's basic building blocks interact under the influence of 4 fundamental forces. Investing billions into such a sophisticated venture might seem like an act of whimsy driven by mere curiosity, yet the potential returns are tremendous. By dissecting the particles that form all matter and deciphering the forces that govern their interactions, scientists are paving the way for groundbreaking developments in technology, healthcare, and energy. Central to the Large Hadron Collider's quest is the Higgs boson, often dubbed the God particle. This elusive boson is vital because it relates to the Higgs field, believed to endow particles with mass. Without the Higgs boson, particles would lack the mass needed to form the universe as it exists today. The Large Hadron Collider's ambitions extend beyond the Higgs boson. It also aims to detect signs of supersymmetry, a theory proposing that each fundamental particle possesses a heavier counterpart known as a superpartner. The appeal of supersymmetry lies in its potential to fill numerous gaps in the Standard Model, particularly offering insights into dark matter, which, though invisible and unreflective of light, comprises a significant portion of the universe's total mass. Finding these supersymmetric particles could help physicists answer some of physics' most complex questions, such as why gravity is so feeble compared to other fundamental forces, or how particles gained mass shortly after the Big Bang began. Moreover, the Large Hadron Collider investigates the quark-gluon plasma, a state of matter that likely existed right after the Big Bang. By colliding lead ions, the collider recreates this plasma, enabling scientists to study its characteristics and understand how it evolved into protons and neutrons. These experimental discoveries could one day translate into practical applications. For example, the inception of the World Wide Web at the European Organization for Nuclear Research that houses the Large Hadron Collider revolutionized data handling needed for particle physics research. Similarly, advancements made in the Large Hadron Collider's superconducting magnets and precision detectors could eventually benefit sectors like medical imaging and computing hardware. Constructed between 1983 and 1988, the Large Hadron Collider's vast underground tunnel, stretching 17 miles with a 12.5 feet diameter, is buried about 574 feet below the surface, ensuring minimal disturbance from external vibrations and a stable, cool, operational environment. The tunnel's robust walls, fortified with steel and concrete, also provide critical radiation shielding during particle collisions. Above ground, the Large Hadron Collider is complemented by extensive surface facilities critical to its operations. These installations include sophisticated control electronics, powerful compressors, and effective ventilation systems. Integral to these operations are the cooling units, which manage the immense heat generated by the collider, maintaining safety and operational integrity. Annually, the Large Hadron Collider produces approximately 15 million gigabytes of data, illustrating the scale of its scientific inquiries. Handling this massive data volume required a robust computing grid, an international collaboration of thousands of servers distributed across numerous data centers worldwide, which processes, analyzes, and stores this data efficiently. This grid supports data management and facilitates global scientific collaboration, allowing researchers from various continents to work together seamlessly. The data from the Large Hadron Collider's experiments test various particle physics theories, including the properties of the Higgs boson and the search for new particles, potentially revealing the universe's fundamental constituents. When particles collide within the Large Hadron Collider, they generate new particle showers captured by detectors. These events are digitally reconstructed using the vast computing power of the grid, allowing scientists to analyze the interactions in detail. Beyond theoretical research, the Large Hadron Collider's computing advancements also propel developments in grid computing technology, finding applications in diverse fields like medical research, climate modeling, and complex simulations requiring substantial computational resources. Cooling such a large system is a feat in itself. The collider uses liquid helium to keep its superconducting magnets at temperatures near absolute zero, colder than the void of space. This extreme cooling is crucial as it allows the magnets to maintain their superconductivity, efficiently directing high-energy particle beams through the collider's extensive ring. Safety at the Large Hadron Collider is paramount. The tunnel's thick walls and advanced shielding materials contain the radiation emitted during collisions. Numerous safety protocols, including fail-safes and monitoring systems, protect both the machinery and human operators. Focusing on the Higgs boson, often portrayed as a phantom-like entity due to its elusive nature, the Large Hadron Collider was specifically designed to capture this particle en masse, akin to setting an intricate trap for a creature long speculated about but never observed. The Higgs boson is pivotal for understanding why particles have mass at all. However, the Large Hadron Collider's mission is broader than just hunting the Higgs boson. It also searches for evidence of supersymmetric particles, potentially explaining dark matter and filling out the Standard Model's limitations. Additionally, the collider probes possible extra dimensions as suggested by theories like string theory, which could provide insights into the fundamental forces, including the enigmatic gravity. Despite its groundbreaking potential, the Large Hadron Collider's journey has been marked by challenges, such as the 2008 magnet malfunction that led to a significant helium leak, damaging the collider and causing a lengthy delay. Yet from 2009 to 2013, the Large Hadron Collider conducted experiments that ultimately confirmed the Higgs boson's existence. This monumental achievement in physics validated a long-standing theory and opened new avenues for scientific exploration. After its initial successes, the Large Hadron Collider underwent upgrades to enhance its collision energy capabilities, allowing for more precise experiments and exploration of new physics realms beyond the Standard Model during its second run from 2015 to 2018. The collider's third run began in April 2022, now operating at an even higher energy level, promising to uncover deeper cosmic secrets and potentially redefine our understanding of the universe. On July 7th, during this current run, a dramatic event occurred when a crack developed in Earth's magnetic field, resembling an unexpected breach in a dam. This geomagnetic storm, which lasted 14 hours, allowed solar winds to penetrate the atmosphere, creating spectacular auroral displays far beyond their usual high-latitude locations. These auroras are not just a natural light show, but also indicative of our universe's dynamic and continually evolving nature. They result from the interaction between the Earth's magnetic field and solar winds, consisting of charged particles from the Sun. Such phenomena provide stunning visual effects and essential data about solar activity's impact on Earth, which can influence satellite operations, electrical grids, and even climate patterns. Discover the cosmic events that create the northern lights and hint at the universe's deeper mysteries. The northern lights of stellar puzzles. The northern lights, while a stunning spectacle, often overshadows the European Organization for Nuclear Research that houses the Large Hadron Collider phenomena that trigger them. These events, known as co-rotating interaction regions, are massive plasma structures formed by the collision of solar wind streams of varying speeds, similar to two merging rivers creating a turbulent waterfall. The National Oceanic and Atmospheric Administration noted the exceptional strength of this storm. Despite the beautiful auroras and the apparent calm among experts, the reality of these geomagnetic disturbances is potentially alarming. Earth's magnetic field serves as a protective barrier that deflects solar winds and more severe solar emissions, which could otherwise disrupt satellites, sensitive electronics, and power grids' stability. Usually, geomagnetic storms are brief, closing as swiftly as a window shut against a storm. However, recent storms have been more persistent, resembling a door that closes slowly and allows more time for charged particles to infiltrate our magnetic defenses. This extended duration can wreak havoc on contemporary technology. In 2003, scientist Harold Frey likened our planet's magnetic field to a drafty house, which mostly keeps the storm out, but occasionally lets some energy leak in, causing disruptions. These breaches in Earth's magnetic shield let streams of charged particles hit the Earth. These particles can induce ground currents that interfere with underground pipelines, accelerate corrosion, and disrupt power stations. The potential damage extends beyond mere power outages or communication disruptions. It affects the infrastructure essential for urban life. For example, a significant geomagnetic storm in March 1989 caused the Hydro-Quebec power grid in Canada to fail, leading to a 9-hour blackout affecting several million people. This incident highlighted the vulnerability of modern electrical grids to solar disturbances and prompted improvements in forecasting techniques. Satellites face high risks during these storms as increased radiation can degrade their components, shorten their operational lives, or completely disable them. It's like navigating through a hailstorm without protection, where continuous bombardment can cause critical damage. Furthermore, this radiation poses a serious risk to astronaut safety, potentially jeopardizing missions and causing long-term health issues. Airlines sometimes reroute flights to avoid the high radiation areas near the poles, leading to increased fuel use and operational costs. Radio communications also suffer. High-frequency signals used by aircraft, ships, and military operations can get lost in the storm's interference. This isn't just inconvenient, it's a potential safety hazard where timely communication is crucial. Understanding and predicting these storms is vital. Hence, organizations like the National Oceanic and Atmospheric Administration continuously monitor solar activities. Their Space Weather Prediction Center employs sophisticated tools to forecast solar winds and storms, helping to mitigate potential impacts on technology and infrastructure. As we near a period of heightened solar activity, as predicted by solar cycle forecasts, the need for improved preparedness and response strategies becomes critical. The anticipated increase in intense storms calls for enhanced global readiness. The increased sun activity is important to the European organization that runs the Large Hadron Collider and lets scientists study the sun more closely. This helps them predict future changes in the sun and get ready for any effects those changes might have. Though the recent geomagnetic storm did not cause immediate radio blackouts or power failures, the vivid auroras across Canada and the US were a clear signal of the sun's ramped-up activity, which was more intense than expected for the current solar cycle. This suggests that aurora enthusiasts may enjoy more frequent and spectacular displays in the near future. Our nearest star's unpredictable nature showcases its ability to both dazzle with beauty and disrupt with force. In the midst of these cosmic events, human ingenuity probes the universe's secrets through grand endeavors like the Large Hadron Collider. Often described as a massive microscope, the Large Hadron Collider allows scientists to explore the smallest particles of our universe. Following its 2017 highlight revealing properties of the elusive Higgs boson, the Large Hadron Collider has continued to make significant discoveries. By 2021, it had identified 59 new hadrons, and in July 2022, it observed a novel particle, the pentaquark, consisting of unique quark combinations. Located deep under the Swiss-French border, the Large Hadron Collider uses powerful electromagnetic fields to accelerate particles to near light speed. These particles are smashed together, and the collision debris helps identify new particles like the pentaquark. This process not only confirms the existence of predicted particles, but also occasionally reveals new, unforeseen aspects of particle physics that challenge our existing knowledge. The Large Hadron Collider's experiments are carried out in a circular tunnel 17 miles long, where environmental conditions are tightly controlled to resemble the vacuum of space. This isolation is crucial to ensure that the only interactions recorded are between the particles themselves, without external interference. The tunnel is cooled to just above absolute zero, necessary for the superconducting magnets that guide the particles along their collision path. Annually, these experiments generate about 15 million gigabytes of data. Handling this immense amount of information requires a global network of thousands of computers, which work together to process and analyze the data. This vast computational effort is key to distinguishing the extraordinary from the ordinary, such as spotting rare particle events among billions of mundane collisions. The data and discoveries from the Large Hadron Collider have wide-reaching implications in physics and other fields such as medicine and materials science. For instance, advancements in Large Hadron Collider detector technology have improved PET scan imaging techniques. Understanding fundamental particles like the Higgs boson could eventually lead to novel materials or energy sources, which might transform industries and aid environmental conservation. The Large Hadron Collider is also undergoing upgrades to significantly increase its collision rate and data collection capabilities. This high-luminosity Large Hadron Collider, set to start in 2026, will enable 10 times more collisions, vastly increasing the chances of observing rare cosmic phenomena. This upgrade highlights the scale of human curiosity and our relentless pursuit to understand the universe's fabric. Continue into the heart of the Large Hadron Collider, where subatomic particles collide and unveil secrets of the cosmos. From particle collisions to cosmic revelations at the Large Hadron Collider. Within the complex network of tunnels that house the Large Hadron Collider, a veritable storm of subatomic particles races at nearly the speed of light, smashing into each other with incredible energy. Here, in this scientific tempest, researchers face the daunting challenge of sorting through billions of particle interactions. Their tool of choice, a refined computer system aptly named the trigger. This system meticulously selects just a few hundred of the most telling collisions per second to study further, much like the European Organization for Nuclear Research that houses the Large Hadron Collider photographer who sifts through thousands of moments to capture the perfect shot. The trigger's critical function is to identify those rare events that might illuminate some of the universe's most deeply held secrets, akin to a miner panning for gold. The Large Hadron Collider itself operates like a giant microscope, magnifying the minutiae of the subatomic universe. This monumental machine is on a quest to discover particles that have yet to be observed, particles that are theorized to be the titans of the atomic scale. These formidable entities are expected to decay into smaller, highly energetic particles that mark their existence not subtly, but with a resounding presence that the Large Hadron Collider's sensitive instruments can detect. Currently, in its third run of experiments, the Large Hadron Collider aims to capture these undiscovered superheavyweights, the potential behemoths of the particle world. The hope is to directly observe these particles as they decay, which would not only confirm their existence, but also help bridge the gap between theoretical physics and empirical data. Such discoveries could profoundly deepen our understanding of the universe's fundamental structure. However, scientists are tempering their expectations with a dose of realism. The likelihood of directly discovering these heavyweight particles is slim in this current phase. Instead, they anticipate finding indirect evidence, subtle hints, or fleeting shadows that suggest the presence of these hidden giants. These clues, though less dramatic than a direct observation, are invaluable. They lay the essential groundwork for future experiments and might lead to more significant breakthroughs in understanding the universe's arcane laws. Each proton collision within the Large Hadron Collider's vast, circular tunnel, stretching 17 miles beneath the Swiss-French border, represents a potential moment of discovery. These collisions, occurring at energies higher than any previously achieved in a laboratory setting, mimic conditions just fractions of a second after the Big Bang. The debris from these collisions, consisting of many newly formed particles, offers scientists a snapshot of the primordial universe. The Large Hadron Collider's sophisticated arrays of detectors are key in capturing and analyzing the byproducts of these high-energy collisions. The amount of data produced is truly staggering, equivalent to about 700 billion pages of text each year. Handling this data is a formidable task. The Large Hadron Collider's trigger system screens millions of collisions every second, singling out the few that might reveal new phenomena or validate theoretical predictions. This exacting selection process is crucial because the extraordinary is often hidden within the vast mundane. By isolating the anomalies, researchers can piece together the puzzle of how the universe's fundamental particles interact, which has implications for everything from the fabric of space-time to the origins of mass itself. Beyond its search for new particles, the Large Hadron Collider also investigates theories that extend beyond the well-trodden path of the standard model of particle physics. One such theory is supersymmetry, which posits that every known particle has a heavier superpartner that has yet to be detected. Discovering these superpartners would not only revolutionize our understanding of the universe's material basis. Still, it could also provide clues about the mysterious dark matter that invisibly makes up much of the cosmos's mass. Dark matter, which constitutes about 27% of the universe's mass energy content, interacts with visible matter through gravity, but is otherwise undetectable by conventional instruments. Its presence is inferred from its gravitational effects on galaxies and light across the cosmos, an invisible architect shaping the visible universe. The Large Hadron Collider searches for dark matter by looking for missing energy and momentum in particle collision debris, which might indicate that dark matter particles were produced but escaped detection. researchers explore various potential dark matter candidates, such as weakly interacting massive particles, WIMPs. These hypothetical particles are believed to interact with regular matter through gravity and possibly weak nuclear force, but not through electromagnetic forces, which explains why they don't emit light. If the Large Hadron Collider can produce dark matter particles, their detection would come not from observing the particles directly, but from observing the effects of their presence, such as discrepancies in energy and momentum conservation in collision events. This indirect evidence would be a groundbreaking discovery, offering tangible proof of dark matter's existence and opening up new avenues for understanding the universe. However, detecting these signs is immensely challenging due to the background noise of regular particle interactions that can mimic the signals scientists are searching for. It requires precise detectors, sophisticated data analysis techniques, and a bit of scientific intuition to distinguish between a potential dark matter signal and mere statistical flukes. Another intriguing aspect of the Large Hadron Collider's search involves particles that could mediate between dark and ordinary matter, potentially decaying into dark matter particles under the right conditions. If they exist, these mediator particles will help flesh out our understanding of the dark sector, which includes all substances that interact predominantly through gravity. Despite the formidable technology and intellect deployed at the Large Hadron Collider, dark matter remains a spectral presence, seen in the influence it exerts, but not in any tangible form. This ghostly quality makes it one of the most tantalizing subjects in modern physics, representing a profound challenge to our understanding of nature's fundamental workings. This quest is not limited to the Large Hadron Collider. Observatories and laboratories worldwide are searching for dark matter, employing techniques ranging from underground detectors shielded from cosmic rays to telescopes that observe the cosmos in wavelengths invisible to the human eye. Dubai is facing an urgent crisis with a massive flood, thanks to the critical magnet malfunction of the Large Hadron Collider. Dubai's flood threatens the flow of life in a city known for its high ambitions and resilience. Both situations remind us of our vulnerability and the immediate need to tackle and overcome these critical disruptions. They highlight the importance of being prepared and adaptable to nature's power and technological uncertainties. Is the massive investment in the future circular collider justified, or could these billions fund better scientific projects? Like, comment your thoughts and subscribe for more science debates.